So yeah, I have to say, David Beasley made me both feel proud that I kind of understand what's happening in PyPy and bad because it's not actually that hard. This is both an advanced, listed as advanced and on the expert track. So if you don't know what PyPy is, this may not be the best talk for you. However, David's keynote, which I wasn't expecting, probably prepared most of PyCon for this. I'd like to start with a joke which I stole from a presentation I saw by Kenneth Wright. And he quotes our favorite line from the Zen of Python: if the implementation is hard to explain, it's a bad idea, except PyPy. Okay, so I'll start with the overall design principles of the PyPy JIT. One of the most important ones is that it's interpreter agnostic. We do not actually have a Python JIT. We have a JIT generator, which generates JITs for interpreters written in our Python for the PyPy translation toolchain. So this works pretty well, but the JIT generator is not perfect and it cannot generate a fast JIT immediately, or the fastest JIT. So we have to allow the language implementation, the interpreter, to be able to help the JIT with type inference, for example. And our JIT in PyPy is a tracing JIT, which means that we take to heart the idea that 90% of your time is spent in 10% of your code. And we compile only the code which it seems like is being run repeatedly through the interpreter, which means hot functions or loops. And optimizing dynamic languages for assembly generation is a bit different than static languages like C. I'll talk about optimizations later, but essentially what we do is we have to remove all the indirection, which is in dynamic languages. Because in Python, you get lots of power from being able to dynamically assign attributes to instances, for example, but it also adds a lot of interpretation overhead. And the last thing we try to do is make our JIT fastest on code which is simple and idiomatic in Python. And so, while you can put a million different types in a list, that code is not necessarily going to be the fastest on PyPy JIT. Also things like introspection, like introspecting the stack frames and debugging information is not the fastest on the PyPy JIT. So the several components of the PyPy JIT, which I'm going to be talking about, is translation, where we actually generate the JIT from the description of the interpreter. And then I'm going to talk about how the JIT works at runtime, specifically tracing, how we optimize the result of tracing, and assembly generation. So to add a JIT to your interpreter in RPython is actually very simple. You just need to modify your interpreter source to add two special functions which the RPython translator will later recognize. And I'll show you later how this works in the Python interpreter. The two hints are called canInterJIT and JIT merge point. JIT merge point tells the JIT when it's safe to return to the interpreter. And usually that's at the head of the bytecode dispatch loop. And canInterJIT surprisingly tells the JIT when it should enter. And this is at the beginning of loops, once a loop has been closed when we can enter. And the JIT also needs some arguments, which is basically the data which the interpreter is working with. And these are classified into two categories: green variables and red variables. And green variables are constants. They never change during the loop. And so here, let me show you what's in the Python interpreter. So on the Python interpreter, the constant arguments are the code object and the instruction pointer, because when we enter the JIT, those are always going to be constant for a given loop. And then the reds are the frame object and the execution context. In the Python interpreter, the frame object is an object which stores the local variables and the value stack for a Python frame. And the execution context stores thread local data, basically, like exception state. So this is a simplified view of how we have inserted the JIT hooks into the Python interpreter. That while true loop is the bytecode dispatch loop. So we have a JIT merge point every time we go to dispatch a bytecode. And the jump absolute bytecode is a Python bytecode which tells the interpreter to jump to some other bytecode, and it's at the end of loops. So that's how we know that we've ended a loop. So to get a JIT, we have these hints in the source, and then we go to translate our interpreter. And as Dave Bealey said, what happens is we have the interpreter halfway through translation in a bunch of low-level flow graphs. They're in a modified singles assignment form, compiler intermediate representation, and they have low-level type annotations on them. Like it says, add these two integers, or add these two floats, or access some value of a structure. And so what we have this flow graph description of the interpreter, and what we do is the JIT generator takes these and it basically serializes them into a representation which we can write into the binary. So what happens at runtime is we'll have a description of the binary in terms of the serialized representations of the flow graphs, which we call JIT codes. And we'll see how those are used. And so now I'd like to introduce the example I'll be using to show how the PyPy JIT works. It's a very dumb primality test, trial division. But it works well with PyPy JIT because we're really good at optimizing integers. So this is what the bytecode looks like. I just wanted to point out that there's a lot of manipulation of the stack. Like this load fast opcode, these load fast opcodes, they load these variables and they push it onto the stack, and then this operation will pop them off the stack and compare them. And so we're going to see later how PyPy JIT optimizes out all this miscellaneous stack manipulation. So now we have a PyPy binary, and we're running it on some Python code, say my Primality Test. And the runtime part of the JIT keeps a track of every loop and every function call which happens in the interpreter. And once this a threshold is reached with the count, the number of times the loop or the function has been entered, then we enter the tracing portion of the JIT. It's slightly more complicated than that because we want to avoid having massive amounts of compilation at one time, so we slightly fudge the thresholds. So now we're at the tracing portion, and we use something called the meta interpreter. And the reason it's called the meta interpreter is we take the saved JIT codes, the serialized representation of the interpreter, which we generated at translation, and we actually execute it at runtime. So what happens is we have an interpreter for the JIT codes, which is interpreting the interpreter, hence the meta interpreter. And what the meta interpreter does is it records all the operations it executes, tracing the loop onto a giant list. And the values in the program are stored as boxes. They represent low-level types like pointers, integers, and floats. And so the meta interpreter is tracing, and eventually we'll reach the jump absolute bytecode, and we'll know the loop has been closed. And so what we have is a big linear history of the loop or function which we've traced. And it's important to note that the trace is almost completely linear because as the meta interpreter is tracing, it enters all the the calls which the interpreter would make, and it flattens those out into a giant list. So there's almost no calls out of the trace. So I've tried to depict this with a diagram. So the basic idea is you have the Python interpreter, which is running merrily along. It decides to start, the JIT is invoked, and then the meta interpreter uses the JIT codes to run the Python interpreter, and it generates the intermediate representation, which is language which we use, which traces are written in the Python interpreter. One other thing which is important to mention is something called guards. So as the meta interpreter is tracing, it's based on runtime information. We're running one iteration of the loop, basically. So we're going to be making some assumptions. We're not going to be entering every conditional which is in the loop. For example, in the Primality Test, there's the condition which says, if this integer divides and then we're going to leave the loop. And so all the trace after we've taken this conditions would be invalid if that condition was not true anymore. So what we do is we insert something called guards into the trace. And guards make sure that the trace continues to be valid, or it tells us what the trace, under what conditions the trace will be invalid. And so I've listed some of the things which you'll get guards for, like adding integers. You'll get a guard after it that the operation didn't overflow. So this is what the primality test looks in the JIT IR. So this list thing up on the top is the arguments to the trace, and it's slightly obscure what these mean. Basically, they're all values which are in the Python value stack, and the operations of the Python value stack have been removed in this trace. I'll talk about that in a little. So here's these guards here are basically ensuring that that the variables are still defined. They're not equal to none, and we don't get an undefined local exception. So this is completely unoptimized, I have to add. So this is the part where I actually compute the modulo. You can see that already we didn't generate operations for this this load fast operation because we've removed value stack operations. And so you'll notice that the binary modulo operation is rather long and complicated, and the reason for that is a bit technical because the semantics of modulo rounding are different in Python and C, so we have to have some extra operations to correct that. And here's the end of the loop. Basically, we check if we add to the loop counter. Oh, sorry. This is the end. One thing to notice is that this is creating a new integer object, and so it's actually allocating memory, and we're going to be able to remove that. So now we hand the JIT trace off to the optimizer. And JIT optimizations are different, as I alluded to earlier, than classical compiler optimizations. Generally, one reason for this is that we are limited by speed. We don't want to spend 3 seconds optimizing it as fast as GCC possibly could because no one wants the program to stop for 3 seconds. However, we do some basic compiler optimization, strength adjunction. We check integer bounds. But the most important optimizations we do are primarily responsible for removing the indirection in the interpreter, and those are virtuals and virtualizables. So the basic idea of virtuals is that if we have an object which is allocated in the trace that we don't have to and it is not passed to anything else outside of the trace, then we don't have to allocate it, and we can flatten out its fields and perhaps store them in registers or on the stack instead of in the heap. And so
What this does is it not only avoids allocating stuff, but it also it removes boxing. For example, you saw the integer types in PyPy are wrapped in this object called winteger int object. That's actually an object which has to be allocated if you're just running on the interpreter. But we can remove the boxing of that and thus significantly speed it up. There's other thing is virtualizables, and virtualizables are the thing which were responsible for removing the stack access. And they're almost like virtuals, but they're allowed to escape the trace, meaning they might possibly be passed out of the trace, and so we need a lot of extra bookkeeping to keep track of those. And the final thing optimization we do is unrolling. Basically, in the simple case, what will happen is we'll generate 2 iterations of the loop. The first one will compute all the loop invariants, the things which don't change throughout the course of the loop, and it might read some fields out of structures or the frame which won't change over the course of the loop. And then the second iteration, at the end of it will jump to the second iteration, and the second iteration will be completely optimized, and it won't have any of these extraneous field accesses. And so now I'm going to show you what optimizations have done to the primality example with something called the JIT viewer, which is a fun toy which we have for showing JIT IR. So I've made the font really big so it's usually less ugly. So this is the, oh, come on. Sorry, I forgot to start it. All right. There we go. So this is the JIT viewer. It shows you the different layers of the JIT. So we have the source code, the Python bytecode, and finally the JIT IR here. So you can see that the numerous operations which I saw when I showed you the unoptimized version have been removed. No more integer objects are being allocated. And everything can now, when we generate assembly, can be stored immediately in registers and on the stack. So now it's finally time to generate assembly, and generating assembly is surprisingly easy, considering it's Python. And basically, the operations which we've recorded are already so level that we essentially just have to write out the x86 instructions. Our register allocator is not particularly sophisticated. This is mostly because it would be slow, and we're not really at the point that having a fancy algorithm would give giant speed-ups. The other tricky part is the garbage collector. We have to dynamically inform the garbage collector about things which we've allocated in the JIT trace. And so I can show you the assembly on the JIT viewer too. So it's pretty tight. We're doing the division operations directly in assembly, and so that's how it got fast. There's one other important thing. So remember guards. We have all these guards which are protecting the trace and the assembly from valid runtime conditions which it was not prepared for. And so these are also inserted in the assembly. And so if one of these fails, we don't have any assembly which could run for it, so we have to go back to the interpreter. And this is kind of an intricate process because a lot of stuff has been optimized out, and there's values sitting on the stack which need to be wrapped into Python objects and stuck back into the interpreter. So we have a special place when we're generating assembly, we generate a special place where we jump to if a guard fails. And there's a compact description there of where everything is on the stack and in the registers, and then we're able to rebuild the interpreter state from that. And It's almost that easy, except we can't jump right back into the interpreter because the assembly might have been corresponding to someplace in the middle of a complicated opcode. So what we do is we use the meta interpreter to interpret back to the JIT merge point, which is the head of bytecode dispatch. And then when we're there, we can safely jump back to the interpreter. And the meta interpreter, when it's doing this function during guard recovery, is called black hole interpreter because it eats everything. It doesn't record any tracing. Of course, this is kind of inflexible if we were only ever able to JIT stuff which didn't have any conditions in it. So if a guard repeatedly fails, instead of using the black hole interpreter, we trace to the end of the loop again, and then we've compiled something called a bridge. And the next time the guard fails, we can jump to the bridge, which allows us to remain in assembly. So, as I said before, we have to help the JIT a little bit in the Python interpreter. And so these are some of the ways we do it. One of the ways is that we can tell the JIT, this is probably going to be constant, so you should constant fold based on it, but check to make sure it's constant. And that's called constant promotion. And we've also engineered a lot of data structures which are optimized better by the JIT. A lot of them are dictionaries, probably because the dictionary type is so important in Python. And I'd like to briefly talk about one of them. It's called mapdicts. And what mapdicts are based on the observation that most instances of a class look exactly the same. So what we try to do is we share the layout, the instant layout, where the attributes are of the type. We share that, we put it on the class, and then we can just store the values of the instance in a linear array on the class. And so this is similar to a feature in V8 called hidden classes. And so basically, what this allows us to do in the JIT is that the class is almost always going to be constant. So what it ends up having is attribute access can just be compiled down to a lookup on an array, which is much better than a dict lookup. And so this is a diagram of that. And so the storage is stored independently of the instance. And so to conclude, we're able to generate a fast JIT from our Python interpreters. And we do this by, our JIT is a tracing JIT. And our optimizations seek primarily to remove the inefficiencies and indirection found in dynamic languages. And we're able to adapt to changing runtime conditions with bridges on the loop. And finally, our interpreter is optimized for the JIT with special data structures. Thank you very much. I'll be happy to take questions.
So what's the next step or attack for performance that you work on, or the next goal that you're trying to reach with JITting the code?
Okay, so the question is, what are we looking at next? There's a lot of things to be done. One of the things is integrating it with other PyPy technology. So recently, stackless support has been added to the JIT. Another thing is STM. I think they talked about that at the last talk. We'd like the JIT to be able to help optimize that. And the other prongs of attack are, we're doing some more work with unrolling and bridges. It's actually a bit more complicated than that. We have something called targets, which allow us to unroll in different ways. So we could also do some work on the back end, just making our assembly even tighter.
Early on in the talk, you said, and when we hit the jump absolute, we know that the loop is over. And I thought, oh, I wonder, like, is that an assumption that whenever I see a backwards jump in the generated bytecode, it's because we've seen the end of a loop? And like, how many built-in assumptions are there in the JIT that the bytecodes came out of the CPython compiler, and could I confuse it by handwriting bytecode that did something funny?
Yeah, you could confuse it. Yes, basically the jump absolute bytecode is only ever used in while and for loops. So if that changed, it would probably be a 5-minute change in the JIT, though. So.
I'm working on optimizing some scientific simulations that are already running under PyPy. To optimize further, would you recommend looking at something like the JIT viewer, or how much do traditional profiling tools still apply with the JITting?
Okay, so yeah, the JIT viewer is often helpful. It can take a bit to kind of understand what it's telling you. Profilers, we do have profiler support in the JIT, but sometimes basically what I usually do is I look at the JIT viewer trace and I try to see, okay, what is the JIT getting confused about, and how can I help it? So I guess that's where I'd start.
So if I understand right, most of this JITting is completely independent of Python. Like you could use this to JIT other languages that aren't Python?
Oh yes, in fact, we have several other JITs in the Python interpreter. Like our regular expression interpreter is JITted, as well as several built-ins like filter and map. We've also added JITs too. So.
I thought I had seen that there was like a little toy directory that had, it looked like a scheme interpreter.
Yes, also, yeah, we have some other toys, Prolog, Scheme. So yeah, you could, that's definitely what we want. We want to create a dynamic language implementation framework. So.
Cool, thanks.
Thanks for the talk. Which CPU architectures and indeed subfamilies of CPU architectures are supported? And is it kind of dynamic based on which CPU ID is detected at runtime?
Okay, so we're basically the only thing we detect is SSE, because we need to know if we're going to support floats. Besides that, I think we try to use the square root operations and on some CPUs. So it's not particular. We don't do much with that.
Yeah.
Besides.
And it's x86, but also ARM as well. Anything else? I mean, if I need to support other architectures, am I going to need to patch this? I think the answer is yes. And,
if you need to support other, you mean like ARM or something?
or PPC, S390.
I'm a software developer.
I'm sorry.
Yes, ask Armin.
I'm sorry.
Yes, the answer to this question is that we support x86, x86-64, ARM v7 more precisely, and PowerPC 64 is in progress right now.
Thank you.
Thank you. That's what he said. All right. Thank you again.